Here is a quick story about how to find a potential function for a conservative vector field. The one on the screen has two components. It is a conservative vector field. There is a test we can do to determine that it's conservative. I will assume that test has already been performed. We've confirmed that this is a conservative vector field. And so we know we're not wasting our time trying to find the potential function. So the story of the potential function is that there is going to be some scalar function f of xy whose gradient is this vector field. And sorry, my voice trailed off because I thought I wasn't recording, but apparently I am, so it's all good. And so whatever function this is, the gradient of this function must be this vector field. That means that this first component must be the derivative with respect to x of our mystery potential function. So if this is the derivative with respect to x of our scalar function has to have a term 3x in it, because that's where this 3 comes from. It has to have the antiderivative of this with respect to y, which would be x squared y. And then because this is a derivative with respect to x, this mystery function that we're building could terminate in any function of y alone. Could be sine of y, y squared, square root of y, hyperbolic sine of y to the fourth, whatever it is, because the derivative of that function of y with respect to x is going to be 0, and so there would be no evidence of it in this component. So we would write that as, some arbitrary mystery function of y. So we've reconstructed most of the potential function already just from that first component with respect to x. Now we have to go look at the other component and just make sure things match up. So if we take this now and do its derivative with respect to y, we need to ensure that that is consistent with this. Well, the derivative of 3x with respect to y is 0. The derivative of x squared y with respect to y is x squared, and oh look, there's that. So we've already explained all of those terms. And then, from just our mystery template here, the derivative of this with respect to y would continue along with g prime y. So this x squared explains that x squared, and that means that this g prime, this extra little bit of our potential function in progress, is the thing that produces that negative 3y squared. And that means that g of y itself is a negative y cubed. And, there might be an arbitrary constant with that as well. And so altogether, our mystery potential function is now resolved to 3x plus x squared y minus y cubed. I will choose an arbitrary constant of 0. And so now we can see that the derivative of this with respect to x is exactly this first component. The derivative of this with respect to y is now exactly this second component. Boom, done. There's the potential function. Here's a second example, and just to show that it can work in either direction, I'll start with the right-hand component here. So here is a two-dimensional vector field. Let's assume it has been tested to demonstrate that it is a conservative vector field, so again, we are not wasting our time looking for a potential function. So this time I just have to remember again, whatever my potential function is, this component is the derivative with respect to x, and this component has to be the derivative with respect to y. So this time, I'm going to start with this side, and I'm going to understand that this component must be the derivative with respect to y of our potential function. So what does our potential function have to have in it automatically? Well, this is the derivative of a term with respect to y, which means that the original potential function would have had y e to the x. so that the derivative of that with respect to y would give us this e to the x. And oh, look at that. There's that term sitting there when we look at the derivative with respect to x. And then this second term, the derivative of this with respect to y, sits here. Sorry, this term is the derivative of the potential, is from the derivative of the potential function with respect to y. So the original term must be x times sine of y. And then, if we just double check, derivative with respect to x of this term is just sine of y, and looky there. So just with that investigation, all four terms in the in the vector field are explained. So we don't even need to mess with that possible arbitrary function of x over here, because we've already explained everything up here, and boom, done, there's the potential function. If you have a three-dimensional potential function, vector field, I mean, it's the same overall process. You just pick one, probably the first one. Understand that this first term is the derivative with respect to x of your mystery potential function. So use that first component to reconstruct most of your scalar function. You might have some extra pieces added on, and so there you bounce back to the y derivative and the z derivative. And just make sure that you can set it up so that everything is consistent. It's quite a bit of trial and error, but it's usually very straightforward.